In this video we will discuss the opportunity that listening to rivers can provide in the field of river monitoring. We take the novel approach to use the sound we can all hear beside a flowing river, the burbling, gushing noises, and relate this to river stage. This research was made viable with the help of Durham University, Evoto, the European Regional Development Fund, the Northern Powerhouse, and British Society of Geomorphology. I will talk on why we use sound as a monitoring method, how we gather this data and process it, and what are the possible causes of any relationship that we find. Imagine sitting by a river. What can you hear? The gentle burbling of the river? Now imagine when being there when it is during a storm. That burbling river becomes a thunderous torrent. It is by this assumption about rivers that they get louder the higher the river stage is that we base our research on. The main question we hear is why use sound to monitor a river when there are already established methods for doing so. Looking at the standard methods for data collection, the main system used are pressure transducers, which are anchored to the river and require infrastructure to be built. There are also ultrasonic depth monitors, which lean over the channel itself, meaning it requires an uninterrupted line of sight, and also image-based systems that require illumination at night to view stage boards, with significant battery drainage if off-grid. Sound eliminates these drawbacks to these established methods. It does not need to be placed within the water, it does not need a direct line of sight, and it can work equally well at night without additional features. As long as where you place the monitor is close to the river and you can hear the river, then sound is a promising solution to site safety and cost effectiveness. When recording sound, there will always be noise pollution, whether it be the dawn chorus, a vehicle driving by, or someone talking as they pass. These intermittent sounds are concerns but will be a lesser extent during storm events. The main environmental noise source is by wind and rain. With wind we have the issue of blowing out the microphone, and with rain creating splashing noises. For river sound to be used, we need to identify these sounds and remove them from the sound of the river we are after. To view what sound data looks like, we can visualise it using a spectrogram. Recording each of these signals individually, we can see the characteristics of each, with the trills of the bird's song to the high amplitude Brownian noise of wind, with the river itself as background noise, constant. To isolate the river, we assume that the river will be omnipresent in any recording. We develop the lowest median filter to pick out a sound value for a specific recording. This is achieved through the splitting of an audio clip into 1 second windows, with 0.5 second overlap between them. Each window is processed using a fast Fourier transform, changing the data from the time to frequency domain. The window is then split into kilohertz bins and a median taken. This is done for all the windows in the recording, and with each bin then having several median values. Under the assumption that the river is the base noise, the lowest median is then chosen. Here we have an example of an unfiltered versus filtered example of the 1 kHz bin from the hot whistle burn over a series of months. We call the resultant river sound data a sonohydrograph. It is clearly visible that the filter vastly improves the fit of the data to the actual recorded stage from a pressure transducer. When we plot our sound values against its corresponding stage value, we see that a relationship can be formed. By plotting a logarithm, we are then able to see how well our relationship fits the data. Comparing between unfiltered and filtered data, there is a dramatic increase in the fit. When determining how long to record for, we need to assess the site with it either being exposed or not. Comparing the exposed kill-up burn to the more sheltered hot whistle, we can see that the longer we record for, the better the relationship between sound and stage if plotted against one another and a log taken. The most significantly impacted frequency range is the 1 kHz region, which is shown in the dark blue line, as this region is most affected by wind. We can see that the longer a recording is, the better the relationship is found. For sound data to be a surrogate for traditional methods, it has to work in the toughest of conditions. Storm Ciara and Dennis were a once in 20-year storm event to hit the UK in February 2020. During these storms, we had sound monitors located at Environment Agency monitoring stations. With a reliable source of stage data, we are able to see how well sound performed against this established method. Our first column looks at what the best frequency is to use. by seeing how the R-squared relationship changes over frequency. The second column then compares between stage and sound, with the third showing a comparison between the river stage and sonohydrograph. It is clear that with our data from Storm Kira, that in each river we see a relationship between sound and stage. In each river we show the height of the largest roughness element, such as a boulder. We believe that this is what generates our sound relationship, with varying sound as obstacle gets submerged. Having shown that we can gather stage data from using sound, we need to assess what is generating this relationship and if there is a way of determining what sound a river will produce over varying stages. Commonly, flumes may be used to address features such as this to enable full experimental control. However, sound would be difficult to measure in these circumstances. We therefore used a whitewater course to examine the link between roughness element size and distribution against varying stage. The T's bars enabled us to build large obstacles within a channel and control the flow. By running the course with different obstacle configurations, we are able to assess if obstacle size has an impact with sound. Our preliminary data is suggesting that roughness element height does indeed influence heavily the sound-stage relationship, with obstacles that are around the same depth as submergence being the loudest. More interestingly, having more than one obstacle of the same height or different configurations, the sound-stage relationship is nearly consistent. We believe this shows that submergence of obstacles is part of what causes sound to change with stage, and to a lesser extent the configuration of them. To conclude, we have discussed why sound is a novel approach for river monitoring, how we process the sound data, and what may be causing the trends we see. When assessing the usefulness of this technology, it has to be considered in the benefits it may bring to some places that require some sort of monitoring. Using sound as a method for measuring a river is a novel approach to remotely monitor rivers. Established methods of gathering hydrometric data are not going to be abolished thanks to this, but can work in harmony with a larger catchment scale network envisioned, made up of several Internet of Things devices that each work in their own specialised sector. Sound can fill in the gaps where other hydrometric stations cannot be deployed, either due to infrastructure or cost.